Hi. Last time we explained how can we find the response of a system to an input like unit step input or any input, but this lecture we're going to focus on how can you find the response of linear time invariant system to a periodic signal when the input is periodic signal, like you see in here on the screen that the input x of t, it look like square wave and repeated each period t. So how can you find the input in this case? Well, here you're going to apply what you learned before in the course. Fourier series. Any periodic signal can be represented as a Fourier series. So in this case, you can use, for example, exponential one. So x of t in Fourier series is equal to the summation over k ck e to the power of j k omega naught t, and omega naught is the fundamental frequency, right? And you can calculate from the period where it's repeated. Like, I mean, if this is the period t, so omega naught, it can be calculated using the t, all right? It will be equal to 2 pi over t. So that's the fundamental component. That's the input x of t. So using Fourier series, the input can be expressed as a series. And let's just, expand this one equals C0 plus C1 e to the power of j omega naught t plus the second one C2 e to the power of j2 omega naught t. Let's take another one, C3 e to the j3 omega naught t, and then you can continue. So now the input is expressed as a series of components. Each one has a specific frequency, multiple of the fundamental frequency omega naught. You have omega naught, you have 2 omega naught, 3 omega naught, and so on, except the first term, the DC. Now, how can you find the output? Great. You know h of t, and this is the impulse response in time domain. Using Fourier Transform, you can convert it to h omega. And omega is the frequency. And since now you have different frequencies, so you can express omega as k omega naught, multiple of omega naught, the fundamental. So we can put here k equals 0, or k, so let me just write for you. You can have, if you put k equals 0, so you have the impulse response at h0. If k is equal 1, you are with the fundamental h of omega naught. When you have k is equal 2, that would be equal h of 2 omega naught. So it's varying with the frequency, and you're choosing the component like you have in the input. All right, so now we have the impulse response in frequency domain, and you want to find the output. Well, if you have the equation x of t like that, you multiply by h. So I will say now your y, or the output here, that you are going to calculate, you multiply the impulse response by the by h, by the, or so you say y of t. Now you multiply by h, so you have c naught h naught plus C1 and H omega naught, because you put k equal 1, e to the j omega naught 2. Let's take another one. C2 will be H2 omega naught, e j2 omega naught t. The third one, C3 H3 omega naught, e j3 omega naught t, and you can continue. So that will be your output. All right, and you can find the output for each component. You may write this like this is your y naught, and that's your component of for fundamental, y1, y2, y3, and so on. So you can find the output as a summation, and of course this is by applying superposition. So simply, let's just say, in this problem, if the input is periodic, you are going to express it as a series of harmonics or component using Fourier series. And you can use, we use here exponential Fourier series. And also, since the system is linear time invariant system, you are going to use superposition. What does it mean, superposition? It means you are going to apply each input separately, and then you find the corresponding output, and in the end you are going to sum them or you add them. That's how you apply superposition. Let's take a numerical example so you can feel how can we do that. All right. Let's now assume that the input is a square wave. And we'll sketch the input here. Start from 0 to 1, and then 2 from 1 to 2 is equal 0. Then you start again to repeat it. Three, and also. All right, so that's enough. And the height is equal 10. So it's a square wave, and that's the input. The first step, expressed in Fourier series. How you do that? First, the period. You have to find the period is equal to, it's from 0 to 2, so it's equal to second. Accordingly, you can find the fundamental frequency, which is omega naught is equal to pi divided by the period. So 2 pi divided by 2 is equal pi. So omega naught is equal pi. Then, to express in using Fourier series, that's the expression x of t is equal to ck e to the power of j k omega naught t summation from k minus infinity to infinity. All right, and we like to separate c naught when k equals 0, because when you have both k equals 0, you have c naught and e power 0 equal 1, and then you make the summation where k is not equal 0, the other value you take it. So you have ck e to the power of j k, and substitute by omega naught is equal pi t. So that will be your Fourier series, and you can find the value of c naught and ck. That's what you're going to do. C naught, you find c naught. How you find c naught will be 1 over t, the integration from 0 to t, x of t dt. Accordingly, you have the period is equal to 2, it's 1 over 2, and then you are going to integrate from 0 to 2, but from 1 to 2 is equal 0, integrate from 0 to 1, and the function is equal to 10 dt, so you get 5. So that's, the value of c naught. You want to find ck, I will just show you the beginning and save your time. How you find ck is 1 over t, the integration from 0 to t, x of t e to the power of minus j k omega naught t dt. I will start it, so 1 over 2, and from 0 to 1, and the value is equal 10 e minus j k, and omega naught is equal pi t dt. You do the integration, and you find in the end, just to save your time, I found that it's equal 0 when k is even, and equal to 10 over jk pi when it's odd. So that's, the ck. So obviously you have the input expressed in series. Let me just write the expression for you. So you have x of t is equal c naught is equal 5, so that's equal 5, plus the summation. I will take the first 3 elements. When you put k equal to 1, so when you put equal to 1, it's odd, right? So you have 10 over j, and k equal 1 j 1 pi, and it's multiplied here by, you substitute by k equal to 1, so it'll be e j pi t. All right, and now you go for the second even is equal 0, so you don't take it, you take, this is by the way for k equal 1, just to remember, and that's for k equal 0, that's c naught. And then you'll go for k equal 3, so you put 10 over j 3 pi e to the power of j 3 pi t. If you want to continue, you have 10 over j 5, you take 5 dot e j 5 by t, and so on. So you used Fourier series to express the input as a series of harmonics. Now you want to find the output. Well, the system has to be given, the impulse response have to be given. All right, so let's say, assume that's given, if the impulse response of the system was given as h of t equal to e to the power minus 2t ut. All right, this is given. You should convert this using Fourier transform to the impulse response into frequency domain. And this is, I mean, easy. We did that before. If you know the formula that e to the minus at ut, its Fourier transform is equal 1 over a plus j omega. I'm going to use that, and a is equal to, so it will be equal to 1 over 2 plus j omega. So that will be the impulse response given in frequency domain. Great. So now what do you have? You have the input expressed as a series, and you have the transfer function, and I want to find out. Let's say that in the problem or this example that we are giving said that find the amplitude of the first and third harmonics in the output. Well, so they don't want the whole thing. They are focusing on the first and the third. So how can you find that? Well, we'll say that the output y of t, you have the input, let's say that you have the DC x0, and you have x1, and you have x3, and you have x5, and so on in our example. That's all will be multiplied by h omega, all right? And h omega, it's changing, so you will have x naught h naught plus x1 h times h omega naught plus x3, we don't have the second, h3 omega naught, and so on, all right? For the DC component, this is, I mean, the DC component will be y naught, and that will be the first, and that will be the third. And that's the question asked about. Let's find y naught. What's y naught? It's the DC component of the output. That's the DC component of the output. It's equal to x naught h naught. X naught, the DC, is equal 5. So that's equal 5. What about h? Well, h naught, we got h of omega. That's h of omega. Let me write it here. H of omega is equal 1 over 2 plus j omega. So you put omega is equal 0. When you put equal 0, it will be 1/2. So h of 0 is equal 1/2. So the output will be equal to 2.5. So the DC component of the output of the system will be 2.5. Let's find the first component, y1. That's the first harmonic. Or sometimes, I mean, they call it the fundamental component, because it has the fundamental frequency omega naught, right? So that will be equal x1 h omega naught. x1, we have it here. That's x1. 10 over j pi, 10 over j pi, e to the power j pi t. That's all x1. H omega naught, I have h omega, so I substitute by omega naught, and you know omega naught is equal pi. So that will be equal to 1 over 2 plus j pi. Because omega naught is equal pi. We found that in the beginning of the problem. So that's y1. And if you want to find the amplitude, we can find the amplitude of this one. Just will be some mathematical simplification. Let me work with you. I mean, this the first one. Well, 10 to the power of j pi, and you have e to the power of j pi t. That's that's not outside the magnitude. Then you add here 1, 2 plus j pi. So that will be the coefficient of a j pi t. So you need to find the magnitude of this one. It's like a complex number, and you can find the amplitude if you want to find the amplitude of the fundamental component. So the amplitude of the fundamental component, you can do it by MATLAB, but just I'll show you now how can you do it by your hand here. So the amplitude of the fundamental component is equal 10 over pi, and the amplitude of the second 2 square plus pi square square root, and then you multiply and find that component. All right. Well, let's now find the third. If you find the third component, y3, it's equal the third component of the input, and h omega is going to be replaced by 3 omega naught. x3 will go back to x. That's the third component. 10 over j3 pi. 10 over j3 pi e to the power j pi 3 pi t. That's all x3. h3 omega naught, we know it's 1 over, let me just show you, to remember. That's, h omega. You replace omega by 3 omega naught, and omega naught is equal pi, so 3 pi. 1 over 2 plus j 3 pi. So y3, the third harmonic, equal 10 over j 3 pi times 1 over 2 plus j 3 pi. That's the old amplitude. I took the amplitude here, and e to the j 3 pi t. So that's the amplitude. Let me just take the magnitude. You will have the amplitude of the third harmonic will be equal to 10 over 3 pi 1 over 2 square plus 3 pi square square root. So that will be the magnitude of the third component. All right, and then we'll be done. If you need the fifth or whatever, just this is the way to do it to find the response of